Hello and welcome to our next lesson. You might be wondering, is Mr. Foster a Cowboys fan? Why do you own a Cowboys jersey? But if you look a little bit closer, actually, this is not just a Cowboys jersey, but a Dak Prescott jersey. And why might I own a Dak Prescott jersey? Well, where did he go to school? But the fabulous Mississippi State University. I bet you didn't realize that Mr. Foster went to school with Dak Prescott. That's right. And so obviously people in Starkville are obsessed with Dak because he's done so well. So that's why I got this actually for my wife, but it's too big, so I wear it for things like this, I guess. So that's why I own the jersey. Still not a Cowboys fan, but that's okay. I have no ties to the Cowboys, except for Dak, I guess. But moving forward with our topic for the day, it's resonance and harmonics. And so those are related, but we'll start with resonance and then kind of launch into harmonics from there. So what is resonance? What resonance means, the idea of resonance, it's the reinforcement of a sound wave due to reflection or vibration. Basically, we saw how waves reflect or bounce back in previous lessons, right? So if you make a sound and it bounces back and the two waves interfere with each other, but constructively, right? Reinforcement, constructive interference, that would be resonance. And we'll look at some examples of that. So, like, one main example that you guys are probably familiar with from resonance, what resonance is just the idea of breaking glass using just the sound of your voice. If you've ever heard of someone trying to do that, it's not very easy because the idea is that you have to be producing a certain frequency, a certain precise frequency, so that the waves hit the glass and they interfere constructively with the vibration of the glass to the point that it shakes itself apart, basically, that it shakes itself apart and shatters. So that frequency that you have to find is called the resonant frequency. All objects have a frequency at which they want to vibrate at naturally. So if you expose them to that frequency, they vibrate, and if you can keep that up, they start vibrating more and more and more, and end up vibrating uncontrollably. And that's what causes the glass to be shaken apart, is because you're hitting it with the same frequency consistently, so it shakes more and more and more and more, and then breaks. So glass is a common one. And I said everything has a resonant frequency. So this is an example you might have seen also. This is a video of the Tacoma Narrows Bridge, I believe is what it's called. It's known as Galloping Gertie for obvious reasons right here, right? So it's a suspension bridge over this canyon, and the idea is that wind was hitting it in such a way that it was resonating and doing those undulations and vibrating, and it resonated, it got bad enough that it actually shook itself apart. So it's not just small things or specific things like glass, but everything actually has a resonant frequency. And resonant frequency is also known as a harmonic frequency, which is how we connect to the rest of our things. So sound waves, like I said, standing waves are really important in musical instruments. And so what you're doing when you were, if you've got a trombone and you're changing the length, or you've got a clarinet and you're covering up certain holes, what you're doing is you're changing the harmonic frequency at which the instrument is resonating at, and that's how you're producing a sound. Guitar strings also do the same thing. Any instrument really is operating off of this because they're producing sound waves. You're making resonant frequencies, and so we have a few ways to model these musical instrument setups. We usually model them as like a column of air. Imagine like the inside of a tube of air, basically like the inside of a flute or something is what we look at for our model. And those come in a few varieties. There's closed. I guess I'll start drawing these here for you guys. So a closed setup. The closed basically means that the ends are closed off. And so here we'd have like our two walls are the sides of the tube basically. And then these are the openings on the side. But in a closed setups, both of the all walls are closed here, so they look like that. Now this doesn't make tons of sense with like an instrument, like a wind instrument, because how do you blow air through it if both of the sides are closed? What this really represents is more of like a guitar string setup, or like a string oscillator, where we've seen like Move with the Slinky. both the ends are closed. Basically, there's no air flowing through it. So close is really like a string slinky oscillator setup. So that's what this looks like. Now, what happens is that the sound wave is resonating inside of it. So it's producing a standing wave. And so we use these setups to draw different kinds of standing waves inside of our air columns. And they have specific rules for each setup. So for closed, you've got two closed ends. And so remember, a standing wave looked like this if drawn on top of each other, right? It looked like that, and then just continued on and on. So when drawing this inside of the closed setups, since the walls are closed, you have to draw a closed end on each side. And so that means that it would look like this. See how both of the ends are closed? We have nodes on the walls because it's closed. And nodes correspond to closed, but it also just like looks like it's closed on that side, right? The wave comes together to a point and it's closed on that end. So you have nodes on the walls for closed. Our next one is open. So we have our two walls here, and then we're just leaving these sides open, right? Because it's open. Lots of instruments use this kind of setup, right? Imagine like a clarinet where you're blowing across the hole and there's the other ends open as well. And so for open, both of these sides have to be antinodes. They have to be open. So what does that look like? It means that we have an opening here and an opening here. So we can connect these to look like this. You see how both of those sides are antinodes, or they just look like they're open, right, instead of closed. And so I think that's a pretty good visual for how you're drawing this in a open setup. Last but not least, we have closed open, affectionately referred to as clopen. So closed open or clopen looks like this, where we have one side closed, one side open, right? So on the closed side, right, we have a node, and on the open side, we have an antinode. So it would look like this. Boom. That's how you see how it's closed on this side and it's open on the other side, right? Closed on the closed side, open on the open side. Node on the closed side, antinode on the open side. So those are our basic shapes for them. But we can actually go into a little bit more detail because there's actually multiple harmonic frequencies for for each of these shapes. So on page 2, we get into the different harmonic frequencies. There's multiple frequencies at which these are resonating, and we can draw multiple different shapes for these. I just drew the simplest ones for our examples. So we start off with closed, and we're looking at what's called the first harmonic. So closed, first harmonic. Closed looks like this, right? And on each this is basically the same shape that we drew before. So first harmonic is the simplest shape that we could draw in our closed tube. So the simplest point from here to here is what I drew before, right? With no extra squiggles. It's just that. And so this is our first harmonic. It's the simplest standing wave for closed. And so an important thing when talking about these setups is how the wavelength of the wave relates to the length of the tube you're working with. So this tube right here has a length of capital L, and wavelength is lambda, right? So we're trying to figure out how the length of the tube relates to the wavelength of this wave, right? So how much of a wave do you see here in the tube? So it goes from up back to the middle point, right? But a whole wave is an up and a down, right? So this is only the up part. So this is half of a wave, right? So the rest of the wave would be, there would have to be another up right here, right? So this inside the tube is half of a wave, right? So our length, L, is equal to 1/2 of the wavelength, right? Because this is half a wave inside of our length L, right? Or you can write this the other way around, where wavelength is equal to, if I just move the 2 over, right, is 2L, right? So our wavelength of the wave is twice the length of the wave because we have half a wave inside of our 1L, right? So that's for our first harmonic. As I move forward, I think maybe you'll see the connections here a little bit more. So we'll move on to the second harmonic. Second harmonic, close, close. So the way that we go up additional harmonics, basically, if you can just keep increasing the frequency at certain points, and you'll get new harmonic frequencies. So for the second harmonic, we're drawing the second simplest shape that we can get, where we have two closed ends. So the easiest way I think to draw these is you just take this first harmonic shape here, and then you just draw it 2 times because it's the second harmonic. So this is the shape that we've got, and then we draw it again, side by side. And so that's our second harmonic. Notice we're still closed on each side, right? And so there you have it. That's our second harmonic. That's what it looks like. So how much of a wave is inside of this length? We get one full up and down, right? If we had half a wave before, we have a full wave now because there's one full up and down, right? It goes up and then down. Remember that these are just 2 waves, two of the same images stacked on top of each other. That's why it looks like this, right? If you need to like rewatch, I had a little animation at the end of the previous video that kind of made that clear. But basically this is one full wave, one full up and down, right? So our length here is equal to the wavelength. They're the same, right? One full wave fits inside this length. Lovely. So our third harmonic. Our third harmonic, closed still. So it's our third harmonic, so we just take the first harmonic shape and draw it 3 times. 1, 2, 3. Boom, and that's what our third harmonic looks like. So how much of a wave is here? If you're keeping track, we had 1 wave inside, right, and we added another half. So we have 1.5 wavelengths, right? We have 1 full up and down, and then another just an up or just a down. So that's 1.5. Our length is equal to 1.5. Another way of writing that is 3 halves, right? 3 halves of a wavelength. 1.5, just 1 more than 2/2. Or if you're writing this the other way, wavelength is equal to 2/3 over L. It's nice to have both of those relations because you can kind of use whichever one you might need for a situation. Last but not least, we have fourth harmonic. So still closed, and it's the fourth harmonic, so we draw 4 of those shapes, right? 1, 2, 3, 4. It might, if you're following the pattern here a little bit, we've added another half a wave, so now we have 2 full up and downs inside of our length, right? There's 1 here and then 1 here. So our L is equal to 2 times the wavelength. We have 2 full wavelengths inside of our length L, or if you're writing the other way, lambda is 1/2. Great. So that's what our fourth harmonic looks like. And then right down here at the bottom, leave myself very much space here to write it, but I'll write it over here on the side because I have some space next to the second. So, and here at the bottom, I've written nth harmonic. So what that means is we can actually, using the formulas that we have, we can figure out a formula that would tell us these length versus wavelength formulas for any harmonic, any n harmonic, right? Whether it's n equals 5, the fifth harmonic, n equals 6 for the sixth harmonic. We can use this formula that I'm about to show you, and that we can figure out from here actually, how to figure out the wavelength and length relationship for any harmonic. So let's look at our pattern here. We're looking at the wavelength versus length relationships on the right side. So we have lambda equals 2L. We have lambda just equals L. This would be like 2/1 for the first harmonic, right? This would be 2/2 for the second harmonic, right? Lambda equals 2/3L for the third harmonic. This one's lambda equals 1/2, aka 2/4L for the fourth harmonic, right? So if you're following our rule here, our wavelength for some harmonic n, some n harmonic is 2/n divided by L, right? We take the number of the harmonic, whether it's the first harmonic, we plug in a 1 and we get 2. If we plugged in a 2 for the second harmonic, right, we'd get a 1 here. If we plugged in a 3, we'd get 2/3. If we plugged in a 4, we'd get 1/2, right? So this is our rule here for a closed. 2 pi, or sorry, why is it pi? lambda equals 2 over n times L, times whatever n harmonic you're looking for. If you were looking for the 10th, right, you'd have 1/5 L, for example. So very helpful formula we have there. And that's all that there is for closed. So our next one that we're looking at is open. So I'll erase this real quick. Make me some more space. So open. We basically followed the same process here. It's just with a new shape. So for our first harmonic, right here, our open setup looks like that. And so we have to have antinodes on each side. It has to be open on each side, right? So it's the shape that I drew was the simplest way to get from point A to point B. It's just like this. This is our simplest shape we can draw here. So that's our first harmonic. So how much of a wave is here? Well, it starts at a different point, right? But we only go from antinode to antinode, or we'd make one like cycle from a up to a down. But remember, a full wave would be up, would be down, and then back up again. So again, this is only half of a wave, right? Because the rest of the wave would look like that, right? You'd have one full up and down. So our length here again, this is our length. We're using the same idea here, length L. Our length L is, again, this is half of a wave, right? Half of a wavelength. Or wavelength is equal to 2L. All right. On to the second harmonic. Open. Same process here, right? For second harmonic, you take the same shape and you're drawing it twice. So we have one squiggly shape and another squiggly shape right next to each other, like that. So that's our second harmonic. So if you're following the thought process, this is going to look very similar to the closed. We have one full wave here, right? Up. We start up, go down, and then we end back up. So we're in the same spot, meaning it's one full wavelength. L is equal to lambda. Length is equal to wavelength. On to the third. Third harmonic, we're just drawing the shape 3 times. 1, 2, and 3 shapes. Great. So we start up, go down, back up, one full wave there, and then we go back down again. So we had 1, and we added another half on it, right? So again, L is equal to 3 halves, 1.5 waves, or lambda is equal to 2/3 L. All right. Fourth harmonic follows the same logic here. 1, 2, 3, 4. Great. So again, we have like the previous setup. We have 2 full waves here, right? 1, 2 full waves. 2 wavelength. L is 2 wavelengths. Or lambda equals 1/2 L. So you might be already seeing the result here because we got the same results as before, right? So again, our rule for this one is that lambda equals 2 over n times L, right? If it were a 1, we get 2. If it were 2, we get 1. If it were 3, we get 2/3, and so forth. Follows our pattern. Makes sense. Great. So fortunately, our formula for open is the same. And it really follows the same sort of logic as closed. It's just drawing a different shape, right? Making sure that you have open ends on your open. All right. Last but not least, we have clopen. All right. Clopen. We'll start again with our first harmonic, of course. First harmonic. Our shape, remember, looks like this. Great. So we need a node here and an antinode over here. I drew the simplest shape for you already, right? Is just to connect these like this. So now we're getting into something different, right? How much of a wave is that? So we start from a middle point, right? And we just go to a top. Before, if we look at our closed, right? The shape we saw looked like this. So it went over and back down to a middle, right? And we said that this is half a wave, but this is just this segment, right? It only goes up the halfway. So this is half of a half, right? Or a fourth of a wave. Because then the rest of your wave would be there. That would be a half. But then you still need this part to be a full wave. So this is actually a fourth. Erase this bit. Fourth of a wave on this one. Got it. So our length L is equal to 1/4 of a wavelength. We can see that this is already going a little bit differently, right? Or lambda equals 4L, right? Just moving the 4 over, multiplying by 4. All right, second harmonic time. Second harmonic. We'll follow the same process here. You're just drawing two of those shapes, making sure that you have a node here and an antinode here. So let's see how this works. So if I draw one shape, it looks like, well, I can't draw this here, right? Because this doesn't line up. There's no continuous wave here if I line up the closed with the open. So that doesn't work. So what if I try to flip it around and I draw it like this? Well, that doesn't work either, right? Because I'm supposed to have an open over here, right? It's supposed to be an antinode. So this doesn't work. This doesn't line up. What's wrong? And that's actually because you're right. It doesn't work. It doesn't work like this. So for clopen, there's actually no such thing as a second harmonic. It doesn't exist because the waves don't line up. It doesn't work. And so that's actually true for any even harmonic. Clopen, closed open, only has odd harmonics because otherwise you get this setup where you don't have a node or an antinode where you're supposed to. So for closed open, for clopen, you only have odd harmonics. So let's check out the third so I can show you. So for the third harmonic, right, we need 3 of these first shapes. So we'll draw that. And then we draw another one but flipped around, and then we draw that. Right, so that works, right? We have shape 1, shape 2, shape 3. So that works. And how much of a wave is that? Well, we have a half wave here, and then we have another of this first shape, another fourth of a wave. So this is a half plus a fourth, which is the 3/4 of a wave, right? Makes sense if we had 1/4 here and we have 3 of those, then now we have 3/4. So L equals 3/4 of a wavelength, or wavelength equals 4/3 L. Astute people might be noticing our pattern already. So, like I said, there's no even harmonics. So if I tried to draw the fourth harmonic here, I'd run into the same issue that I did on the second harmonic. No such thing as the fourth harmonic. We skip on to the fifth harmonic on the sheet if you're following along with the worksheet. So for the fifth harmonic, we need 5 of those shapes. 1, 2, 3, 4, 5. Okay. So we have a setup here that, again, we've got 5 of these first harmonics. So if you're following the logic, then you just multiply a fourth by a 5, you get 5/4. But if we're looking at, we have one full wave here, right? So that's 4/4, and then we add another fourth on, so we get 5/4. So we have 5/4 of a wave here, or lambda equals 4/5 L. Great. So our rule down here at the bottom, we have the nth harmonic, but notice that it's only odds. So for only odds, our rule here, if we see we have 4/1, we have for the first harmonic, 4/3 for our third, 4/5 for our fifth. So our rule here is that lambda equals 4 divided by whatever the harmonic number is times L, right? First harmonic, 4/1, third harmonic, 4/3. Only odds though. No such thing as an even harmonic for clopen. Great. So that's all that I have for this one, is just drawing the harmonics. Because this was, I didn't want you to have to process all this information, then start applying it. So this is where I'll cut this off. If you need to rewatch the drawing of these videos and how we got these formulas, just pay attention to drawing the individual segments, because I think that's the easiest way. Instead of trying to remember what the shapes are supposed to look like, you just take the base shape and then do it that many times for the nth harmonic. I won't make you draw like 20th harmonics, but you draw the shape 20 times. So no big deal there. It'll be. I mean, I probably won't make you draw more than what's here already. You might have to like see one drawn that's more than this and identify it. But we'll work with that in the next one. So I hope you enjoyed harmonics. They're pretty neat. Go Dogs, not Cowboys.